This conference will now be recorded.
Very good evening, students. As we thought that we will discuss and conclude this chapter by today's class. So today we'll discuss the measuring instruments, Wheatstone bridge, meter bridge and potentiometer, or potentiometer bridge also you can say. So these three instruments we'll discuss, and to analyze the circuit and all, here we needed Kirchhoff's law. So that's why it is very useful now to use the Kirchhoff's law here to solve the complicated circuits. So we'll do the application part of Kirchhoff's law today in this Wheatstone bridge. And Wheatstone bridge, a meter bridge works on the principle of Wheatstone bridge, and potentiometer also works on, like, we'll be analyzing using Kirchhoff's law. Okay, so let us see what is Wheatstone bridge. So you can see this figure, this particular circuit arrangement. So there are 4 resistors, right? So 4 resistors arrangement along with the galvanometer. So this is actually a Wheatstone bridge. So it is an arrangement of 4 resistances. See, 4 resistances generally they are named as 4 resistances are generally named as P, then Q, this is R, and this is S. I'll tell you what these are. So Wheatstone bridge was actually devised by Charles Wheatstone. That's why the name is Charles Wheatstone. Okay. And that is in 1843. Okay. So Charles means looks like British physicist or scientist. See here, what are the elements we have? First of all, there is a battery or a cell which has EMF E. You can see that. I'll write this values because these are very small in font. I'll write E, and see there are 4 resistances R1, R2, R3, and R4. Okay, and see these 4 arms are given a name. 4 arms are given names. Like, okay, one more point let me tell you. See the battery, or in this case the battery. Okay, so there are 4 junctions, you can see that. First, second, third, and fourth. So junction A, junction B, junction C, and junction D. So there are 4 junctions. So between B and D junctions, galvanometer is connected. Galvanometer is connected. What is the use of galvanometer? Galvanometer actually determines the flow of current in a circuit. It indicates, actually it can detect whether current is flowing in a circuit or not, or the direction of the current also it can indicate. So galvanometer in general, to identify the current flow, okay, to identify the current flow, galvanometer is used. Okay, in the magnetism chapter, moving charges and magnetism, that chapter will learn the galvanometer in detail, moving coil galvanometer. So in this case, you look, there are 4 junctions A, B, C, D, and see this is very important not to alter these junctions. Like I cannot put A here, okay, because there is a specific specification or specific reason why I should put A here and C here, because the battery or the cell has to be connected between A and C. The cell has to be connected between A and C junction. That is what it is. Okay. And the galvanometer has to be connected between B and D junction. This is always true for any Wheatstone bridge. Okay. So this is what you have to remember, and we should not alter this A, B, C, D junctions, because if we alter somehow, then we have to take care of these things, that between B and D there should be galvanometer connected, and between A and C junctions the cell must be connected. So this is one thing to remember. Okay. See, when generally in a galvanometer there will be arrow. Okay, generally it looks like this kind of a panel analog if you see. So there will be like this, so panel. So this will be zero neutral line. When there is no current flow, no current, this is zero current. So galvanometer, this needle, okay, kind of an arrow that will show here. But if current flows, so this is suppose connecting terminals. So if the current flows, then this will either deflect rightwards or leftwards. Okay, it will deflect either leftwards or rightwards. Okay, so by seeing, this is called deflection. So by seeing the deflection of the galvanometer, we need to understand whether the current is flowing through the circuit or not, or in a particular branch, through a particular branch or not. Okay, if suppose I have a circuit, I have a branch, and in any branch, particular branch, I am just connecting this galvanometer. If this is still, the needle is still, it is not moving or not deflecting, then through that branch there is no current flowing. So this is the purpose of galvanometer over here. Now see, the bridge has, this Wheatstone bridge has something called balanced condition. Balanced condition. So we can use this Wheatstone bridge in, like, at balanced condition. At balanced condition, we can actually use this Wheatstone bridge to calculate unknown resistance. To calculate unknown resistance. Balanced condition, we need to find out what is the balanced condition. Okay, what is the balanced condition or null condition? Sometimes it is called null condition. So balanced bridge is, it is sometimes called balanced bridge also. So balanced condition, at balanced condition only we'll be able to find out unknown resistance. You look here, this four arms of the resistances, R1, R2, then this is R3, and this is R4 or unknown resistance. So this R4 resistance could be calculated using this meter bridge at the balanced condition. Okay, we'll see what is balanced condition. At balanced condition, balanced condition, no current flows, no current flows through the galvanometer. Okay, the galvanometer, no current flows through the galvanometer. So this is actually the balanced condition. Okay, so generally balanced current should be, see, I have, suppose I have total current I1 plus I2, which is supplied by the cell, and at this junction A, it will be divided into two. See, I1 is going, suppose, in this way, like AD, this way, this through this branch, and AB branch, the current I2 is flowing. So at this branch, what will happen? At this branch B, at this branch, at the normal condition of the bridge, see at this branch there will be two uh, two currents flowing. Okay, suppose one is Ig flowing this way. Actually, that I2 current will be actually divided into two parts. One will be this way, another will be this. So I4 plus Ig must have been I2. Okay, so this is actually normal condition. Similarly, in this case also, look here, this current I1 coming from A to D. Okay, then this Ig will make, see, I1 plus Ig. I1 plus Ig will be actually I3 at normal condition. So this is I3, it is said here I3. So Ig plus I1 will be I3, which will be flowing B to C. And after flowing here, see this I4 will add here. See I4 plus Ig plus I1 will be added. So this part I3 is actually Ig plus I1. So that is one here, and I4. So this all three will make how much? So this is I2. So this will be I1 plus I2, like that. Okay. So what I tried to say is that when the bridge is not balanced, then what will happen? There will be flowing current in each branch, and in fact through galvanometer also current will flow. So at balanced condition, no current will flow, or no current flows through the galvanometer. That means Ig is equal to 0 at balanced condition. So this is actually the condition for balanced bridge. Okay, balanced bridge. This condition is called balanced bridge condition. Okay, or balance. Okay, balanced condition. So at this condition, look what will happen. See, since current is not flowing, I can say VB will be, VD will be equal to VB. I hope you agree with me. So that is why there is no potential difference between B and D. That is why current is not flowing through this, right? If there is no current flowing through this G, then see, I'll just erase everything. I'm sorry. If no current is flowing through this, what will happen? See, this I2 will be exactly equal to I4, and here I3 will be exactly equal to I1, because no current is flowing through this Ig, sorry, this galvanometer, no current is flowing. Okay, so then see, this I2 itself will go from A to B, B to C, and from here A1 will go to D, D to C. So this will actually complete the circuit. Okay, and at this condition, you know, VB will be exactly equal to potential drop or potential difference between this B point and D point will be 0. So that is the condition. Okay, okay, I have got the conditions. I'll just now uh, go for some numerical calculations. So let me clean this portion. So I have learned already. I can do in two ways. I'll show you how to do. See, VB is equal to VD. This I can write. So VB I can write I2 into R2. If you see, I can write VB is equal to I2 into R2. And VD I can write I1 R1. I1 R1. Okay. Similarly, from here, what I can write? I2 R4, that is equal to I3. I3 means I1. I1 R3. This I can do, isn't it? So now R2 by R4 is equal to R1 by R3. Or in other words, see, I have to find out R4, right? So R4 can be written as, okay, one more point, let me tell you. See, generally in many books you may be able to see. See, the AB branch is called as P, resistance P. Then AD branch is called R. This BC branch is called Q, which is unknown resistance. And this DC branch is called actually S. It is called S. Standard resistance. Okay, standard resistance which is known, which I know. R1, see this R1, R2, or P and R, these are also known. This is standard resistance, maybe a resistance box. Okay, and this is unknown resistance Q, where I have to find out. See, I have got R2 by R4, that means P by Q, P by Q, and then R1 by R3, that means R by S. So this is very, very standard form of balance condition. This is very, very general and also well known to everyone. So P by Q is equal to R by S. This is the condition. Now I have to find out what? I have to find out Q. So what is Q? Then P by R into S. Okay. Hope it is all right. Yes. So P by R is equal to S. This is the way we can use this Wheatstone bridge to calculate unknown resistance. Okay. See, this I have done in some way. Okay, I have just written I1 like I1 R1 etc etc. So this is P by Q. So I'll write this P by Q is equal to R by S. Okay, so this is the condition. Let me find out this particular condition, balance condition or null condition or balance bridge condition for the balance bridge using Kirchhoff's law, because we have learned that very recently. So I'll take two loops, loop 1 and this loop 2. Okay, loop 1 and loop 2. See, I can keep like this. I'm just, suppose I'm going from A to B, B to D, and D to A to B, B to D, and D to again A. For this loop, what we'll write? See, we'll write here voltage of, see, there is no cell in this loop, that is fine. So it will be equated to 0. I2 R2. Then see, in this branch there is no current. And see, this current, I am going from B to D. Okay, B to D there is no. So D to A, I am going D to A, but current is flowing from A to D. So I have to take I1 minus R. So sorry, this is P. R2 is P actually. R2 is P. This is equal to 0 because there is no EMF, no cell. So look what I can write, P by R is equal to I1 by R2. Okay. Similarly, if I see, I go from B to C, C to D, and D to B again, D to B again. So for this loop, look, I can write, I write in terms of Q. I can write I4, which is nothing but I2 into, see, I2, I'll write I2 only, I2 into Q. Then see, this resistance is in the opposite direction. Then I3 into S, this is equal to 0. Okay. So I3 is nothing but I1. I3 is nothing but I1, because no current is flowing through the galvanometer. So I1 by I2 will be again what? Q by S. Right? Q by S. So this is equation number 1, this is equation number 2. If I equate them, then what we get? P by R is equal to Q by S. Okay, this can be rearranged. P by Q is equal to R by S. So this is the condition for balance bridge. P by Q is equal to R by S. I am again and again telling you that you must be remembering where the P branch, resistance P branch is situated, that is between A and B, where the battery is situated between A and C, where the galvanometer is situated between B and D, where the anode resistance Q is situated between B and C, where the standard resistance is situated between D and C. So these are the points we should actually remember, because we will compare in frequently we will be doing problems with Wheatstone bridge, or in the with the application of Wheatstone bridge we will solve meter bridge problems. So in that case also we have to be a little bit careful. So what we get? Balance condition, balance bridge. So I'll write after all this. So this is P, this is Q, this is R, and this is S. So P by Q is equal to R by S. Now I have got a meter bridge. A meter bridge actually works on the principle of Wheatstone bridge. Okay. And what is this used for? This is used for measuring resistance of unknown wire, unknown uniform wire. Okay, look, you can see in this figure, this is actually the meter bridge. Okay, meter bridge. And see, in this meter bridge, what are the things? Actually, see, I have PQRS, like say my P, then Q, then R and S. I should keep this in mind and I should compare. Okay, look, this between B and D there is a galvanometer. You can see this actually. Between B and D there is galvanometer. Fine. Between A and C, between A and C, this cell is there. Okay, now we have to see between A and B what was there. Between A and B there was P. So here P is equal to R. Between B and C, what was there? There was Q. So Q is here actually your S. Now similarly we have to see what is R and what is S. Okay, so it is used to find unknown resistance of wire, and you can see there is a uniform wire of 1 meter length. You can see that this is 100 centimeter. I don't know, this should have been given 100 centimeter meter scale. This figure, the scale is actually not up to 100 centimeter. I'm sorry for that. So it should be 100 centimeter actually. This should be 100 centimeter. Okay, so here look, this wire, what is the wire? See, this is the wire, this is the wire, and these are actually metallic connector. These are L shape and this is I shape. And see, it is making, see, there are two gaps between AB and between BC. So in between A and B, so this resistance is actually okay. This is from resistance box actually. This is from resistance box, and this AS is actually a standard resistor. Okay, standard resistor. All right. See what will happen. I have to find out what is the actually aim here. I have to find out the resistance of this 1 meter wire. So in this case, if I want to use this condition, balance condition, P by Q is equal to R by S, so we have to find out the null condition or balance condition of the meter bridge also. So how do you do that? See, first of all, this wire, on this wire, this arrow is actually saying you this is actually jockey. Jockey. What is the work of jockey? The work of jockey is to slide over the this wire, over the wire all the way from A to C, and make a contact. Okay, make the contact. Like, see, in this case, suppose I have already told you what is P and what is R in P and Q in this case, but what is R and S? See, this point, this is actually jockey which can slide over the wire. So why do we need to slide? Because we need to find out the balance condition. Okay, so suppose it is balance condition at D point. It is balance condition. It is maintaining, or it is actually showing balance condition at point D. So this AD here, actually AD, see, AD is what? AD is actually R here. So we have got AD. See, this length I can find out from the scale reading up to D, and this much also we can find out from the scale reading. Okay. All right. So the jockey is to make electrical contact. So in this case, see, AD, where this null condition or balance condition is found, AD, this much distance. So this AD, suppose it is actually, not suppose, between AD, what is the resistor? So AD will be R. What is the resistor? See, between D and C, this is standard. It is here actually kind of a standard. AS is equal to 100 minus L2. And see, this, suppose the length of the wire is such that, or so when the galvanometer through no current is flowing through the galvanometer, then what happens? This thing, see, R we have got, S also we have got, this is SLO1. Okay. So in this case, see, I have got R, S, and all those things. If I write P by Q is equal to R by S, so P by Q means R by S is equal to R by S is equal to P. Okay, R by S is equal to, that means this is P by Q. P by Q is equal to R by S. Original R by S. Original R A D, between A and D is L. Suppose L by BC. BC means actually in this case between D and C. Between D and C, actually L minus 100 minus. So P, see, P Q, P by Q, P by Q, that is equal to R by S here in this circuit, is equal to R by S. R means here, sorry, R means PQ by RS. R means this between AD, whatever it is. So that is here, it is L1. And L1, suppose there is resistance per unit length is L. See R1. So there also it will be R1. Okay, so with this, see, this can actually get cancelled. All right. So now what we get? We have to find out what is unknown resistance here. We have to actually find out unknown resistance R. See, this will be unknown resistance here also. If we know the A length and all, you can find out unknown resistance also in this way. The R is equal to okay. So I think I have messed it up a little bit. I'll just clean this, and or maybe in the next page I'll write it. So what we had got, R by S is equal to L by 100 minus L. Okay, or R is equal to, R is suppose unknown resistance, then we can find out into S. S is the standard resistance set. Okay, so if we, yes, this is fine. So this is actually unknown resistance. This is the way we can use emitter bridge. Let us do one thing. Let us just take one numerical example so that our knowledge will be little bit concrete. I'll just write this formula somewhere. R by S is equal to L by 100 minus L. Okay, so I have a numerical problem here. I'll just tell you what is given and what we need to find out. See, there is a meter bridge given like this. So I have a cell of 4 volt, 4 volt. I have to have 2 gaps, as you know. This is jockey. There is a galvanometer connected here. G. See, this side it is given. I'm sorry. Just a minute. I have not drawn the wire itself. This is the wire. So galvanometer connected like this. Okay, so there is galvanometer over here, G. Okay, this is the thing, and what is given is, say, this suppose D point, this is B point, as you know, then this is A, this is C, you know that, right? So battery is connected between A and C, right? So what is given is that this is suppose X, unknown resistance, this is R given, 2 ohm. Okay, and then this is 60 centimeters, say 60 cm, then this will be 40 cm, obviously. This is 4 volt. Now what we have to find out, calculate the total current supplied by the battery. Calculate the total current supplied by the battery. So how to find out the total current supplied by the battery? Okay, so here one point is given, that assume that the resistance per unit length of the wire, resistance per unit length is given, suppose smaller. Resistance per unit length is given. Resistance per unit length is given as 0.02 ohm centimeter. Okay, so what will be the resistance of this AD branch? So AD branch will be, what is this AD? Between A and D will be R, PQR. So this is R is equal to 60 meter. 60 centimeter into this resistance per unit length. So I'll just multiply so that I get the resistance of that. So this is R by L, 6R by L. All right, so AD and then DC. Similarly, this is 40R by L. So here we know, at see, no current is flowing through the galvanometer. At that time you have to find out the total current. So look here, I have to find out, see, this between A and D. This is between A and D. So this is between A and D is R. Between A and B, between A and B is what? That is RP. So X is actually P here. Between D and C and A and D. Okay, between BC, what is that? Between BC is Q. So between BC, what is there? BC actually, that is PQ, PQ, that is Q. BC is Q. Two ohm. AB, BC 2 ohm. Then AD 60R by L. Oh, I'm sorry. Yes, 60 R by L means this is 100. L is 100. And this DC is actually, so this is actually say P, we have got PQ. We have got PQ. Then AD is actually R and DC is S. So I'll be using P by Q is equal to R by S. So P by Q means what? P is X by Q means 2. And then R by S. R is how much? 60 R by 100. S is DC. This means 40 R by 100. 100 and R will be going up off. So these are off. Okay, so X by 2 is equal to so X will be actually 3 by 2 into 3. Sorry, 3 by 3 into 2, that is 3. So resistance will be 3 ohm. Unknown resistance X will be 3 ohm. Okay. So if I get unknown resistance 3 ohm, see all other resistances will be calculated. Okay. So unknown resistance is 3 ohm I have got. Once we have got this, look, I'll just clean this. I have got the resistance for all of them. Okay, so here see I'll read of this. This is A, this is C, this is B, this is D, A, B, C, D. Okay, A, B, C, D, all right. So this is X, which we had to calculate. This is 3 ohm, and here it is 2 ohm. And see, this part is how much? This part is 60. See, 60 by 100 into 0.23. See, 0.23. Sorry, 0.2 into how much? Okay, so I have to actually find out equivalent resistance for this actually. So how to find out this? See this branch. If you just look this meter bridge, so this branch P and Q will be parallel to R and S. P and Q. This is P. This is Q. So this will be additive, and this will be again in series. So this will be. Okay, so we need to check which one is series combination and which one is in. Okay, so in this case actually total resistance will be R equivalent will be 10 by 7 ohm if you see the calculation. And So then current through the circuit will be okay. So it will be actually 4 into 7 by 10, and you have to just do a little bit of simplification, and it will be nearly 2.8 ampere. Okay, I think we'll stop it here for today with this. The potentiometer bridge we'll learn tomorrow, and we'll solve many numerical problems over there. Okay, thank you for your patience. Bye for today.